In lab 1, there is going to be 8 experiments, 9 experiments in lab 1, and 4 in lab 2. This area here is lab 1, next door is lab 2. And I think they're like spread across 2 different semesters. They're not crammed into 1 semester. So without further ado, we'll just go ahead and start it. The idea for you guys is to get familiar with the equipment. I'm not sure exactly what you're going to be doing for your assignments. That will come later, the specifics and details. But if I were you, what I would do is I would take note of any keywords that I'll be using. A lot of them you've heard from the classes, the lectures that we're doing this semester. I will try to relate the experiments to specific relevant information from the course to real-life applications, how it is all finds applications in the petroleum industry. So I guess we can go ahead and get started. We'll go clockwise from here all the way around the room, which is why I'm going to start with this counter here, okay? This experiment is viscosity. You know what viscosity is, right? In common sense terms. Basically, viscosity is a property of fluids that quantifies their tendency to resist flow. Some liquids are very fluid, that means they have low viscosity. Others, like for example, like water. Everything is relative, of course, but water is quite fluid. Now, other fluids will be very viscous, like honey, for example, or cement slurry, compared to water, of course. The level of viscosity can be measured by the amount of time, right? Theoretically speaking, I've never done this before, so excuse me if I'm, making pauses or stop to do drawings and everything. I'll try not to digress into theory much. And like I said, in common sense terms, viscosity is a measure of resistance to flow of any particular fluid. But getting more theoretical and scientific, viscosity is the constant that relates shear stress, which is denoted with the Greek letter tau, and shear rate. They use different notations for that. Sometimes it's gamma with a dot on top. I'm not going to go into details about what that is. So basically, viscosity for Newtonian fluids is a straight line starting at 0. And the slope of this line, slope, will be equal to viscosity, which is denoted with the Greek letter mu. Okay? That's how deep I'm going to go. Viscosity is a straight line for Newtonian fluids. Anything that doesn't look like this is called a non-Newtonian fluid. And the relationship may look like this. A straight line starting not at 0, but at some point here. Okay? Sometimes it's a power law. Something looking like this. It will be helpful to look stuff up on the internet. This is fluid mechanics. You will be learning this in detail in your fluid mechanics course and in drilling engineering. We learn about viscosity and we apply viscosity measurements a lot to drilling fluids. And this is what you'll be measuring here in this lab. This apparatus here, can I get the funnel, the Marsh funnel too? Okay. You'll be doing viscosity measurements using 2 instruments. One is called the Marsh funnel, and the other is called the viscometer. This is not just lab stuff. This guy here is used in the field. We have an undergraduate student in his senior year who's taking this lab right now, and he was very proficient in this experiment because he has like 4 years of mud engineering experience. This is what he was doing in the field. This was part of his job. Basically, the way this experiment is going to go, at least this part, you're going to be filling it up with mud. covering this with your finger, taking a stopwatch, opening the finger, and recording the time it takes. And less viscous fluids will flow faster. Viscous fluids will flow slower. Okay? And then you'll be writing a lab report on all those measurements, converting this time with a given formula into a viscosity in viscosity units, which are centipoise. Okay? This guy here, basically what you do is you fill this metal cup up to a certain level with mud that you will prepare. Okay? And you will lower this, what do you call it, drum? Or, I forgot, whatever. This metal thing here. No? Lower. Then there's several velocity settings, and you will measure, like you will look in this little opening here with a magnifying glass. The dial in there gives you a measurement. At different speeds, it will give you a different measurements that it can be later converted into viscosity. So two instruments to measure viscosity. And that will complete this experiment here. All right? One more comment. Remember how we talked about viscosity in the drilling context. Now, the drill bit has nozzles. Nozzles are basically narrowings because your drill pipe has a certain diameter, which is larger than the nozzles. Whenever you're pumping fluid through a pipe and there's a narrowing, what it does is velocity becomes faster. Velocity becomes faster, and it means it gets more difficult to pump your fluid. Whenever there's a narrowing, you need more pressure at the pump, you need more energy to pump that fluid with a constant viscosity. Shear rate refers to velocity or pumping rate. Okay? So, at fast pumping rates, you want your viscosity to be low. And at low pumping rates, you want your viscosity to be high, to be able to hold cuttings in suspension. Because if your viscosity is low and you stop drilling, the cuttings in the wellbore will sink to the bottom. That's not something you want to happen. You want to keep them in suspension, whether the drilling is in progress and the mud is circulating, or whether you make a pause and stop drilling. You want those cuttings to be supported by the drilling mud. So, non-Newtonian fluids that behave like this, or like this, is the property you want to have in your drilling mud. Lower shear rate means low velocity. So at low velocity, you want the slope or your viscosity to be high, so it can support the cuttings. But at high velocities, you want your slope to be low, like here. See, almost parallel. Or here, both non-Newtonians. So that when you drill fast, your viscosity, when you circulate through the nozzles, the mud has high velocity, high speed. Your viscosity needs to be low to pass freely through the nozzles. Okay? I think I've gone too far into here. All right, so that does it for viscosity here. We're going to go to the next one. No, we're done. Not part of the lab. I'm not even sure if it's being used for research now, so we'll skip this. Remember when we talked about reservoir rocks, we talked about reservoir rock properties. A good reservoir rock, of course in the conventional reservoir development context, would have good porosity and good permeability. Porosity is the amount of void space in any given rock, and permeability is rock's ability to pass fluids through it. A highly permeable rock will let the fluid flow nice and easy through it. The low permeability rock or tight rock will give the fluid a hard time. Okay? So, I will need the writing board again. Sorry. Just jog it after you. By the way, this course, the Lab 1 course, goes hand in hand with petrophysics. I think they retitled the course, now it's called Formation evaluation. Formation referring to the rock.